Hello, for this project, we will do 5 times 5-bit signed multiplication, and the goal of this project is to write a Verilog code module for the multiplication of signed 5-bit binary number in 2's complement representation. And here is our D0 board. No switches is on, so it's no light, LED light is on, and we choose 1 times 1, and there shows 2 to the 0 is equal to 1. These two ones are all positive, and then we choose a minus 16 and minus 16, and this shows us 1, 2, 3, 4, 5, 6, 7, 8, 9, and it's 2 to the 8. 9 minus 1 is equal to 8, and it's 256, and 16 times 16 is 256, and minus times minus is positive, so the most significant LED light is off, that is positive. And then I will introduce my thinking and the Verilog code. Here is my think of 5-bit times 5-bit, and we ignored the first bit of each number, that is the sign bit, and the last 4 bits is magnitude of the 2's complement. So we change this 4 bits in the binary and plus 1 to change this to the unsigned magnitude, and then we use the most significant, that the sign bit times XOR time the sign bit, that we get the final sign, and the magnitude of magnitude after we change this to the magnitude and unsigned numbers, we use this to compute. And the idea of this way is from the book. We use AND gate for 2 numbers, and this is like the M0 times Q0, M1 times Q0, and we write down here. This is the mathematical way to do the multiplication is M0 times Q0, M1 times Q0, and each row is Q0, Q1, Q2, and Q3, and then we sum each of them to get the final answer. In this way, we will sum this row and then to combine with this row and get the result to combine this row and this row. Like we write down here, sum 1 time plus sum 2, and then plus sum 3, then plus sum 4. This will be our final result, and 4-bit times 4-bit we will get 8-bit output, and plus the 1 bit is the final sign bit. This will be totally 9 bits. This is the require of our project, and when we write down the Verilog code, we need to design a 2-dimensional array to define each result of M times Q. So then here is our code of the first way. The first, this is the main module of this code. This is input and the magnitude, and the output magnitude, and final output, and the wires. And this is the row of called X. This is the end of our M and Q, and we also have the input sign of the M and Q. And here we first call the function to the stages here. This is to change the 2's complement magnitude back to the unsigned magnitude. So if it's equal to sign bit is 1, and we do the computation, and if sign is 0, we keep the same, and we do the same as the Q, and then we do the Denver I and Q to use the for loop to compute each and then put it into the array. And then the first way we use the basically call function to compute each p, and then we do the final sign bit for the output, and then we call the function to be the stage 1, and here is the stage 1, and this is our output is unsigned magnitude, and back it to the choose complement. And then here we put each choose complement to the final, and put the sign to the most significant bit. And here we can compile it successfully, and then we have the wave like this, and this we can see it's correct for the computation in binary, and then we use it as n equal to 3, 5, and 6. It's also get the correct number. Like this picture, and then we do the second way to do the multiplication. But in this, we not only use the forward, we also use the half adder to compute. Here is the example of 5 times 5. Here we used else if and else. This is the third part of our code. This is the first part. This is the end of our code. And then we compile it. This is really successfully. Yeah, and then we talk about our delay. This should be first 2 plus 2 plus 1, and this is the first, and then we need to compute the 2 and plus 2 plus 1, and this result times 8. Here then we plus 1, the total delay of our code, this will be 136. Thank you for listening.